Good evening, everyone. My name is Ranjita, and I am a PhD scholar from Department of Computer Science and Engineering, IIT Hyderabad. Welcome you all to Week 6 live interactive session. Today, the topic that we discuss will be on synchronization and critical sections. To get started, can someone confirm if I am audible? Hello. Yeah, thank you. Yeah. So, in the previous class, we have discussed about process and process scheduling techniques, right? Processes and how they are scheduled. In today's session, we will discuss first about interprocess communication. Then, when there is communication between two processes and when there are data shared between two processes, uh, we need to ensure that the common data that both the processes are accessed is synchronized so that there won't be any data corruption or anything. So the first thing is interprocessor communication. So this is majorly used when we are developing large applications and we want multiple processes to do multiple job and then they have to interact between each other and um, to achieve a common goal. So in such scenarios when one process wants to communicate with another process, there are different ways that they can communicate. One is shared memory, another is via message passing, and the third one is via signal. So in shared memory, we have already seen in the earlier classes, right? Processes. Each process will have its own virtual memory space. So in case of shared memory, how it happens is there will be the user space. We will have process one. We will have process two. And there will be a shared memory. This is the shared memory. And between these process, whatever P1 wants to tell to P2, it will be written to the shared memory, and then P2 will read from it, or vice versa. So this is one way of communicating. And so in Linux, you can go through the functions of how the shared memory is created and all. So SHM get, SHM attach. Those are the function calls using which in Linux the shared memories are accessed. So this is the basic concept of shared memory. For example, this particular process is collecting some information and updating some counter here, and P2 is reading that counter, and based on that some action is being done. So this counter value which is there in this shared memory, P1 will be modifying and P2 will be reading. So we have to ensure that when P1 is modifying the value, nobody else is reading or modifying it. So when we have shared memory using which the processes communicates, it's important that we synchronize the access of this shared memory. Another mechanism is message passing. So in message passing, it is more like a kernel shared memory inside a kernel. So we will have user space, we will have process P1, process P2, and in the kernel space, we will have this shared memory. It will be in the kernel space. So we can think this of some message queue kind of a thing. Message queue kind of a thing. And P1, whatever P1 wants to write, P1 will put it in the share memory and P2 will read from it, or vice versa. Whatever P2 wants to write, P2 will put here and P1 can read. So we can assume that some kind of a message queue is shared between P1 and P2, and P1 will using send and receive system calls, the messages will be sent or received from these queues. So this is the idea of message passing. Then another concept is using pipes. Like if there is a communication between a parent and a child, another inter-process communication mechanism is using a pipe. So we will have these are pipes are nothing but file descriptors. So we will have P1 and we will have P2. So pipes are normally unidirectional. So whatever P1 wants to write, P1 will write to the FT, P1 will write to it, and then P2 will read from it. And if P2 wants to write, it will have this will be a new pipe. So in this direction. So we can assume, we can assume that P1 and P2, we have in one direction we have a pipe, and in another direction also we have another pipe. So whatever P2 will put here, P1 will read from here, and whatever P1 wants to put, P1 will put here like a pipe, P2 will read from here. So this is another way of communication between two parent and child process. Okay. And another way is via signals. These are more like a synchronous communication mechanism, like if we want to kill some process, or if some segmentation fault occur, or those uh, mechanism, that is another way of communicating across processes. Why? So as we see that when different processes communicate, they what do we mean by communication? Some kind of a data, somebody like between two processes, it's basically some message or some data or some variable that they are exchanging, right? P1 is writing to some variable and P2 is reading from it, or P2 is also writing to that variable, and then these variables are used for their respective processing. So when such message passing, or when such sharing of memory from which these processes modify happens, it's very important that they are accessed in a synchronized manner. Okay, so that's where the significance of synchronization comes. Okay. So by synchronization, we mean that the access to the variable should be in an ordered manner, so that we will always get the proper output. Let's take an example and see. I think in one of the earlier classes, somebody asked about race condition. We will see that in today's session. So let's see an example program. Okay, program 0, and we have another program 1, and we have a we have a shared variable which is initialized to 0. Now in this program, somewhere down the line, we are doing this counter plus plus, and in this program, somewhere down the line, we are doing counter minus minus. Now, ideally, and now let's assume that it is being executed in a single core on a single CPU. These processes being executed. So it can happen that we have already seen scheduling right in a round robin manner. Let's assume that P1 is executed, P2, P1, P2, P1, P2, like this. They keep executing until they complete their execution. Now, if we look at upfront, if we see that, okay, the variable, there is a global variable that is shared between two programs. That variable is initialized to 5, and now uh, program 0 is incrementing, so the value will become 6. Now P2 will decrement, it will become 5. P1 will again increment, P2 will decrement, P1 will increment, P2 will decrement. So we will see that this value, the expected value is 5. That is what ideally the expected value should be. But it is also possible that it can take the value, the counter can have value 4 and 6 also. So now we will see how it is possible and why synchronization is important. Okay. Now in this typically when we write this in the C syntax counter plus plus, what actually happens in the internally in the instruction form is that first this counter value from wherever the memory location is, it will be copied to a register. Then R1 will be incremented by 1, and then so these are the three underlying instructions that will make counter plus plus happen. Okay. Now this is in the now if we see again, so this is the counter plus plus in P1. Now if we see counter plus plus in P2, again there is another register to which the counter will be copied. Then R2 will be R2 plus 1 and R2. Okay. Now if now here we have seen that there is a context switch happening, right? So if the context switch happens here, like from P1, the P1 stops the execution at this point. Then the scheduler, the timer interrupt happens and scheduler schedules P2. So again here the context switch happen, and if this continues, then the value will be 6 and 5. So this works fine. Now if if instead of here if the context switch can happen at any point in the instruction, it is just that how does context switching happen? The timer will expire, that is the time slice timer will expire and the interrupt will be generated, and interrupt will be serviced as and when the particular instruction is completed. So this is one instruction, this is another instruction, this is another instruction. All of them are individual instructions. So at any point here, a context switch can happen here, a context switch can happen here also, it can happen. There is no guarantee that only once all this three has to be finished and only then the context switch happen. There's no such guarantee. At the end of the instruction, context switch can happen. Same way, it can happen here, it can happen here, it can happen here. Now let's see an example where the context switch happens after this first statement. That is R1 to counter. Now the context switch happens. Now R2 process P2 will execute. and sorry, this is -1. R2 is R2 -1 and R2. Now, after that context switch happens, and then it will start from this place, R1, and now in this scenario, what will be the value? Now here, if we see in R1, the initial value is 5. Okay, this is done. Now we go to process P2. So P2 will again take the value of counter. So R2 will have the value of 5. Then R2 will be 5 minus 1, which is 4, correct? And counter will be assigned with the value of 4. Now this happens in P2. Now P1 will come back here. R1 was 5. After the context switch, these register values will be restored. So now R1 will have 5. Now R1 equal to R1 plus 1 will be executed. So R1 equal to 5 plus 1, which is equal to 6. And into counter, we will copy this R1 value, which is 6. So we got the final output of counter as 6. So instead, so when the context which happen at different point in the instructions, we are getting different value, correct? Now let's see one more example. If okay, if the context switching happening, now instead of R1, let's assume that R2 started with the execution. Okay, R2 started, so R2 equal to counter. Now after this point, context switch happened, and then P1 started with the execution. Now after this statement, context switch happened, and now P1 is resuming. So P1, uh, this will be executed. Now after this, again a context switch happens, and we go back to P2. So sorry. R2 equal to R2 minus 1, and counter equal to R1. Okay. Now in this scenario, if we see here, initially we had R2 equal to 5. Now we go back to this is P2's execution. Now we go to P1's execution. Again, because a context switch happened here. So now R1, again R1's value in the shared memory is still 5 only. So 5 will be copied, and R1 is equal to 5 plus 1, 6, and counter will have value 6. Now at this point, context switch happened, and then we come back to P2. So P2's register will be restored. So R2 will have the value 5. Now R2 is equal to 5 minus 1, which is 4. And counter will be assigned this value, which is 4. So now we saw a scenario where counter is assigned a value 6, counter is assigned a value 4, and counter is also assigned a value 5. So all these values, depending on where the context switching is happening, the values are differing, right? So this situation is called a race condition. This situation is called as race condition. Irrespective of the order of execution, the value of counter is not same. The counter value, the final value of counter is dependent on the order in which the access is taking place, right? The outcome is dependent on the order. And we call this as the race condition. And so this particular instruction, that is this counter plus plus thing that is shared between the place in the set of instructions in the processes that access and manipulate the same data is called the critical section. Okay, the set of instructions or the set of instructions or code in the process that access and manipulate same data is called critical section. So when we have critical section shared between when we have critical sections in different processes, it is important that we um, have some synchronization mechanism so that we can stop the race condition. Okay, so this is where synchronization comes in. So we have to ensure that if P1 have started this particular counter plus plus, so the counter plus plus have this three instructions, right? We have to ensure that if P1 or P2 have come here, they should be allowed to complete this before and the other process going and modifying counter. So this is what synchronization means. So with synchronization, we ensure that only one process will be manipulating the critical data. So by synchronization, only one process at a time will manipulate the critical data. So we need to have mechanism that will ensure this. So in the earlier program, we had P0 and we had P1 and we had their program. We had counter plus plus here. So we put this inside a critical section. So this forms the critical section. And how we ensure synchronization is that before entering into the critical section, we will do some locking mechanism. And once the process exit the critical section, the lock will be released. So that is how this synchronization or is achieved or race condition is prevented. Okay, so the solution or so this is the basic logic. So P1 in P1 also we have this like counter plus plus. This also forms the critical section. So before entering the critical section, some lock need to be taken, and then after you exit the critical section, the lock will be released. So when P0 have the lock, P1 will not be able to enter. So one can enter the critical section only if it have the lock or the token to enter into the critical section. How this is done? There are multiple ways of ensuring this locking mechanism. Before going to this different locking mechanisms or synchronization mechanism, there are some criteria or some requirements to handle this critical sections. One is that uh, when no two process should be no more than one process should be in the critical section. So these are requirements of the critical section so that the processes executes properly and the shared data will have proper value. It will not have any wrong value. Its value will not change as and when the order of execution is changing. So to ensure that we have certain requirements for critical sections. So first requirement is mutual exclusion, which will ensure that no more than one process should be in the critical section at any point of time. Second requirement is progress. That is, see for here like P naught is currently not executing in the critical section. So now when P1 tries to enter, P1 should be able to enter. That's what progress means. So, in another way, if some process is already in the critical section, then it should prevent another process from entering. But if there are no process in the critical section, then any process that wants to enter into the critical section should be able to enter. That is what progress is. And then third one is bounded wait or no starvation. So it means that if some process have asked to enter, like wanted to enter to a critical section, then there should be a bound time, how much time that process has to wait before it actually gets to enter. So it just cannot go on forever. Like if P1 is there in the critical section and sorry, P naught is there in the, this is P1 and this is P2. This is easy. If P1 is there in the critical section and now P2 is requesting to enter, what bounded wait means that now once P2 have requested, right now there is a limit, there must be a limit on the number of times this process will enter into the critical section while somebody else is waiting. So in simple terms, it means that anybody who have requested to enter into a critical section should be able to enter in the next uh, some clock cycles or in the next couple of seconds or in the next time frame. It should not be in a starving mode or waiting forever. So these are, so the locking mechanisms also have to ensure that. So if we design a locking mechanism which can leads to a deadlock situation, like both P1 and P2 is not able to enter, then this requirement is not met. So when we are designing a synchronization mechanism or a locking mechanism, we must ensure that these three requirements are met by the synchronization mechanism. In simple terms, as I told you, by synchronization, what we mean is locking and unlocking. Let's in how this lock is done, we will come to it. So lock and unlock. So we have program 1, program 2. Now we have program 1. What we will do is we will have a lock. Then we will let's put in it counter plus plus. Then unlock. The shared variable is P2. Again, we will have something like this. So what we mean by this is that only if one can get the lock, one should be able to go ahead and update the counter value. So only if a process can acquire the lock, then it can access the critical section. Okay. Now, once critical section is done, execution is done, then release the lock. So, what is this? Who handles it? We will come to it. Okay. These are explicit synchronization mechanism that we have to write when we are writing our application. Okay, so when we write an application with maybe a multi-threaded application that is wherein across the threads we have some global variables shared across and or some global array or heap or hash data structures that are shared across between multiple threads. Then in the application, as an application developer itself, we have to actually take care of these synchronization mechanisms. Okay, so these are explicitly written, but the operating system do provides us the necessary primitives for it. Now we are looking at those primitives. Okay. And these, like we wrote here, local, unlocal, when we write our code, no, we have to explicitly acquire the lock and release the lock once the critical section or the shared variable operations are done. Okay. So only when you have the lock, you will be able to do the operation, that is counter plus plus. So now if you see that, uh, hello. Can you please unmute yourself? Madhushree, can you please unmute yourself? Unmute. I mean, sorry, mute yourself. Right. Okay. So this is about the basic idea synchronization or locking mechanism. Okay, so why we had to do this counter plus plus here? It is a single instruction that, I mean, it's a single statement in the high level programming language, but we saw that this counter plus plus had actually three instructions to achieve this incrementing operation. So this is not an atomic instruction. That is, an atomic instruction is something which is completed in a single stretch. So since these are not atomic instructions, it comprises of multiple instructions, and there is a possibility that scheduling can happen at the end of each instruction. We have to bring in this locking mechanism. Okay, otherwise if the instructions were atomic by itself, then there is no possibility that scheduling will happen in the middle of it and we have to have the locking mechanism. But when we are writing programs in high level language, none of our constructs are atomic. So we need to have the locking mechanism. So now let's see some examples or solutions of how the synchronization can be achieved. Okay, one easy mechanism or one very simple mechanism is to disable interrupt. So we saw that earlier this counter had values of 4, 5, and 6 because there was a because there were in between there were what do you call it, context switches happening. Okay, now if we can prevent the context switches from happening, then this issue will not happen, right? So one solution is to like just before disable interrupt, then just before the critical section, disable interrupt and then enable interrupt. So this ensure that we in the middle of the critical section, there won't be another interference from another process, and there won't be any issue happening. Okay, but the problem with this, from a user level program, we cannot enable or disable interrupts. This is possible only if we are in the kernel level process. Okay, and additionally, it's not suited for multi-core system. Even if we disable interrupt in one core, the other core can schedule the process, and then there could be a issue. Another software solution is I will just quickly skim through. You can get the details in from the lecture. Okay. So one way is to have another shared variable like turn, like we can stop, like process one will take first turn, then process two, like that. So we will have one variable called turn, which is equal to 1. And the critical section will be entered if while turn equal to 2. If turn equal to 2, then you cannot enter. Okay. Otherwise, it goes on. Otherwise, critical section can be entered, and then turn is set to. This is in process P1. And in P2, it will be while 1, then while 1 equal to 1 critical section, and then you make turn equal to, this is lock, this is the lock, and this is the unlock statement. This is the unlock. This is the lock. So even P1 comes, P1 see that initially turn is equal to 1. So before entering the critical section, like while turn is equal to 2, you have to wait. So turn is not 2, turn is 1. So it will come execute the critical section, and it will set turn to 2. Now when P2 starts executing, P2 will see that, okay, while turn equal to 1, it means that it has to wait. But now the value of turn is 2. So P2 will enter the critical section, and once it is done, it will set it back to turn 1. So here, if you observe that this particular mechanism or locking mechanism will ensure that first P1 is executed, then P2, then P1, then P2, and then P1, then P2. Only one of them will be in the critical section at any given point of time. So mutual exclusion is achieved. There is so for example, when P1 is executing, that value of turn is 1, and P1 is executing here. So when P2 see that the value of turn is 1, and it is in the infinite while loop. It's in a busy waiting. So there is a lot of CPU cycle that gets wasted. And also the order in which the process can progress is P1, P2, P1, P2, P1, P2. Now, if P2 gets scheduled first before P1, P2 gets scheduled, P2 will be in the infinite wait. P2 cannot proceed until P1 gets scheduled. So it does not meet the progress criteria. What does progress criteria says? When nobody is there in the critical section, and if one process is requesting, it should be able to enter. Here P1 is not in critical section, and P2 is requesting. P2 is requesting, but when P2 request, this is the condition, and here since turn value is 1, P2 is waiting, even though the P1 is not there in the critical section. So because of this reason, the progress criteria is not met in the solution. Now another solution is to have a is to have another two instead of this was because there was a single variable. So instead, if we use two variables, turn equal to like inside. Do you want me to explain this? Okay. Okay, now if we see that another solution for this could be to is to use two variables, that is to check whether P2 is inside or P1 is inside, and then we will use those variables also. We will set those variables also before the critical section. But in such a situation, what the problem was that there was a possibility that mutual exclusion is not ensured. So, for example, P1 while one while P2 is inside equal to true. In the critical section, then T1 inside is false. Okay, so here we end. So this two forms the lock. This is the unlock. Same way. um, so here we are telling that if P1 is inside, then wait. Then you set the P2. P2 inside equal to set to true, then critical section is entered. Then since it is, we make it false. So here this is the unlock. This two forms the lock. Okay. Here these two statements together forms the lock. Okay. So in this scenario, as we have already seen, there is a possibility that after this while, if a context switch happens and it goes here. Okay, so initially we have both P2 inside equal to false, P1 inside equal to false. Okay, so initially P2 inside equal to true, this is not correct, it is false, so it will come here. Now here, if a context switch happens and before P1 sets that it is inside its critical section, if a context switch happens, then P2 will check that, okay, P1 is not inside. P2 will also enter here. Okay, and it will make it true, and it will, after it comes back, it will come here, and it's so it can so happen that both of them can be in the critical section at the same time. Okay, so there is a so with such a mechanism, though we ensure that progress criteria is met, but mutual exclusion is not met with the solution. Okay. Now, another approach is to put, instead of putting it here, putting this on top of the, putting this flag before the while loop. Okay. So here, there again, a similar problem happens. If we move this instruction, that is P1 inside equal to, sorry, And same way, if we move P2 inside equal to true, what happens if after the statement, okay, if after the statement, if a context switch happens and it will go to P2 and P2 will also set that P2 is inside, and then when it come back to P1, P2 inside will be true, it will go on a loop. Wait. Again, P2 will see that, okay, P1 inside is true, it will also go on a looping wait. So with this solution, we will not achieve progress. Instead, we end up having a deadlock situation. So another solution to such deadlock scenario was suggested by Peterson. This is only the solution is for two processes. So when deadlock like situation comes, Peterson suggests to have one more variable called favored, and this favored can have only two value, either it is one or it 2. So based on the current value, one of the process which is in the deadlock will be favored, and then we'll be able to come out of the deadlock situation. Okay, that was for two process. And another scenario, another algorithm for ensuring synchronization. These are all software synchronization mechanisms. Okay, is the bakery algorithm. Okay, so the essence of this algorithm is that when we have multiple processes like P1, P2, P3, etc., up to Pn, um, we have to ensure that the processes will enter the critical section one by one. Okay, so the essence, the simple logic here is that whenever a process comes, it will see if um, anyone have already requested to enter to the critical section. So whichever process comes first, it will have the value set as 1. So, okay, how the algorithm logic works is there is an array of n process, and initially there is an array of n process. So, we can call it as num of 0, num of 1, num of n minus 1. Okay. So this corresponds to P1, this corresponds to P2, like that, Pn. Okay. So initially all these variables will be marked as 0, and whenever a process enters a critical section, and whenever a process want to enter the critical section, its value will be set to the max of this plus 1. So the first process that comes will have the value set to 1. The second will have the value set to 2. Third will have the value set to 3. The fourth process who comes to enter the critical section will have the value 4, and so on and so forth. And then only one process at any given point of time will be allowed to enter the critical section. That is decided by a logic which will finally take the process with the lowest num value. Okay, of the available value, the lowest one will be able to get into the critical section. Okay, so that's a basic and you can go through the algorithm and learn, but this is how it actually works. Okay, so now I'm rushing through because there are more lot of topics needs to be covered before we go to the previous year questions. Yeah, so these are, as I told you, these are the software synchronization mechanisms that we looked at. Let's once again take a look at that. The first one that we saw, right? Like while 1, while lock not equal to 0 equal to 1, you enter the critical section. Then you make lock as 0, which is so this is lock and this is unlock. The same way for process 2 also. Okay. So, now if you look at this was one of the way we were seeing it, right? So if we see that initially the value of lock is 0 and we are here in P1. Now, if a context switch happens and now we go here. So in P1, we are at while lock not equal to 0. And then P1 will enter it. Then we have a context switch. Okay. Now we again, so this was P1, this is P2. While not equal to 0, P2 will make lock equal to 1. Now P1 will make lock equal to 1 and both of them can enter the critical section, right? So this have happened because these two operations, these two checks together is what is guaranteeing us the mutual exclusion. But unfortunately, they are not atomic. Correct? So because this two has to be atomic to ensure that mutual exclusion can be guaranteed. So, but since they are not atomic, both of the processes entering into the critical section. So in general, whatever software solutions we have seen, that's not normally used. Normally go for in the normal operating systems and all, we go for hardware based synchronization mechanisms like we have the hardware support which provide us with instructions that help us do this locking, which is atomic also. Okay, then on top of this underlying hardware support, the synchronization primitives are built, and these primitives is what we normally use. Okay, so one of the commonly used hardware instruction is the test and set instruction. Okay, so this is an instruction and this instruction will happen in an atomic manner. That is, what we mean by that is once the processor starts this instruction, it will be completed. Nobody else will, no other instruction will be executed, or no context which happens, or that particular memory location which the instruction is modifying, no one will be touching that. So let's see that how this test and set instruction works. So the equivalent of this instruction, so this instruction is basically, if you write it in C, test and set. So we have a memory location, and whatever is there in that memory location is copied to a variable. Then we copy 1 to that memory location, and then we return the earlier value, whatever was there in the memory location. So this is what this test and set instruction does. Okay, now if you see, okay, 1, 2, 3 C instructions are there. How can it be? C statements are there. How can it be done as atomic? So that is taken care. So hardware, the processor ensure that ensures that this happens in an atomic manner. Okay. So what this test and set instruction do is it will read from a memory and it will return the red value, and I mean it will return the previous value and then set 1 to that particular location. So now how we use this for locking is while so while okay. So this is how this particular test and set instruction will be used before entering the critical section. So let me explain it. So there is this memory location here. Okay. So which is having some value x. Okay. So what happens when we invoke this test and set instruction is that this value x will be initially this star L, that is this location. L is a pointer, which means it's a memory location. Star L means content of that memory location, which is nothing but x here. So x will be copied to previous. So let's assume that x is nothing but 0. So initially, so previous will have 0 copied to it. Then we will set this value to 1 and we will return the initially read value, that is 0. So 0 will be returned. So when a process is entering first time, what happens is initially it is 0. Okay, so when this is called, so we have P1 and P2. Okay, now assume that P1 is calling this and P2 also is calling. So when assume that when P1 and P2 both of them call this together, so initially we had a 0. So we had 0. Okay. Now P1 has called. So what will happen? So what is the value in this memory location? The value, the initial value 0 will be copied to previous. 0 will be copied to previous. Then L will be set to 1 and then previous will be returned. That is 0 will be returned. So this will be set to 1 and when P1 calls it, 0 will be returned. So this while test and set ampersand lock, this whole thing will be executed and we will check whether it is equal to 1. If it is equal to 1, it means that someone have already taken the lock. You need to wait. Okay. Now what P1 got is 0, which means that it will come and get into the critical section. Okay. Now, since this whole instruction is atomic, even though P2 also calls the instruction at the same time, P2 will be waiting. Okay. So by the time P2's turn comes, P2 does this test and set instruction. This is already set to 1. Okay. Now when P2 is doing, the value is 1 now. Okay, so previous will have value 1 and L will be anyway having 1 and what will be returned will be 1. So P2 will get 1 as the return value.
So when P2 enters this place, while test and set ampersand lock equal to 1, it is true, right? It will go on waiting until this value becomes 0. So when P1 exits, P1 will make it 0. So when P1, after P1 make it 0, the next iteration of P2 will get the value of 0. And that is when P2 will enter the critical section. Okay, so why this works? If two CPUs execute like in a multi-core environment, if P1 is on CPU 1 and P2 is on CPU 2, if both of them, if CPU 1 and CPU 2 is executing this test and set at the same time, the hardware ensures that test and set does both its steps before the other one starts. So it is taken care at the hardware level. So when both the CPUs like CPU 1 and CPU 2, both of them calls the same instruction at the same time, one of them will complete this before the other CPU starts and do it. So this is ensured at the hardware level. So that's the reason we are able to achieve this. Okay, so this is the hardware support. This is the basic logic. The actual hardware instruction that Intel supports is XCHG. This is the instruction that Intel hardware supports. So this is the equivalent of test and set. Uh, test and set instruction in Intel hardware is XCHG. Okay. So what this do is right. Yeah, so this instruction is also similar only. What it we can write it like uh, it has to this one is register and memory. So the register will have the value and memory is from where we read that. Okay, so if you want to see the how it works is XCHG, what it will do is it will take the address, that is this memory address, then value, sorry. We saw, right? We are setting 1. So that value, whatever value we want. So what happens inside this instruction is this first EAX register will have the value and then this instruction will be called. This instruction, whatever is there in the EAX, okay, and the whatever is there in the address that will be copied to EAX and then whatever value we wanted to uh, set that will be set. So it happens using this single instruction. Okay. Then how do we invoke this? So invocation is like this: acquire lock while one CHG column 1 equal to 0, then you break. Otherwise, you will be in the loop. Now release will be Yeah. Now in the inside the process, how it will be that there will be instructions we will call acquire, then we will have the yeah, acquire log, then we will have the critical section and then we will release. Okay, so this is how the in the program, this is how we will call it. This will be the primitives. These are the primitives that we will be using for ensuring that the critical section will be entered only by a single process. Okay, so this is the normally commonly used mechanism. So on top of this hardware instruction, high level synchronization constructs are built. Some of them are commonly used synchronization primitives. One is spin lock, another is mutex, and another is semaphore. Okay, spin lock is something like so. As I showed you, we will how we will be using it in the processes like sorry in in P1 we will have acquire lock. We will have the critical section here. Then we will have release lock. Same way, P2 will have
acquire and release.
critical section and it will have release. Okay, so one of them will acquire the lock. So the earlier, so this acquire lock is nothing but what we have written here. Okay, so this one and this one. So this is how spin lock works. Okay, so one disadvantage or difficulty with spin lock is that there is this constant, it's checking, there is this constant while loop wherein we check on the what is the current value of lock. So it's like while one is it's there is
बेटे
a
हम तो खाली
while.
आशीर्वाद देंगे हम तो खाली आशीर्वाद देंगे आशीर्वाद से बड़ा कोई गिफ्ट थोड़ी होता है पैसे दे और 11 रुपए देने अरे वो आंटी जो है बुड्ढी वो 11 रुपए दे रही है खाली आती है बेटा 11 रुपए का शगुन लाए हैं
Excuse me, please mute.
यूट्यूब पे जाता हूँ मैं सीधा पहुंच लिया आजा आशुरी नहीं बता
All right. Yeah, so one of the major disadvantage with spin lock is this, like while busy waiting. Okay, so because of that, moreover, because this is a hardware primitive which has to ensure that no other like two processor invoking this exchange instruction doesn't modify the memory. There is a bus level lock that is kept, and when we have this inside the while one, when we keep calling this exchange, this is actually a very huge performance impact. This causes a huge performance impact. Okay, so there is another another version wherein we actually do, instead of having this whole instruction inside the while, we do this once, and then we only check whether the logged value have been changed. So a better and better performing acquire is also possible. But having said that, still there is this while loop is still there. So another mechanism is mutex. Mutex is nothing but it is equivalent to sorry, spin lock. It is same like the logic they acquire, everything is same. It is just that we don't wait. We don't wait in a while loop and keep checking whether the lock have been released. Instead, what we do is we the process. If it see that okay, another process have taken the lock, the process will go for a sleep, and then once the process which have actually taken the lock, it will invoke a wake up. Right. So okay. So there is a small modification made to this program. So instead of what we earlier we had while in the in the acquire part we had while one if xchg of logged comma 1 equal to 0, we break, and that is when we go to the we acquire the lock. Otherwise we go to a sleep here. Okay, so this is in the acquire part, and in the release part, in the acquire, in the release, we make logged equal to 0, and then we do a wake up. So this prevents the busy locking mechanism. So this is what mutex is. It's similar to spin lock. The same primitives and all are used, but instead of waiting and checking whether the lock has been released, the process will block itself, go sleep. Then when the lock is released, a wake up will be issued. So, but one problem with this approach is that if there are like some multiple processes waiting, which is sharing a common data, if there are multiple processes, then there is a possibility that a lot of process will sleep, and like for example some 10-15 of those processes were waiting for the lock, and all of them were sleeping, and finally when the lock is released, wake up is issued, all of them will wake up together, right? So there is, we call this problem as a thundering herd problem. So this leads to a lot of context switches. So how it happens is initially, assume that we had P1, P2, some P10 process. One of them is having the lock. So P2 to P10 is in sleep, which is basically blocked state of the process. Okay. Now, when an unlock happens, when a wake up happens, all the 10 will move to ready. And then, so all of these guys will go to ready state of this. So P1, P2 to P10, all of them will go to the wake up will put them into the ready queue. Okay. Now, when all of them get scheduled, only once, assume that P2 gets the lock again. P2 gets a lock. Okay. Now after that, when P3, P4 and P10, all of them get scheduled, they all will again go for a sleep. Because they went to this ready, they have to again, they go to the running. Sorry, I missed that. They go to running, and during the running, they will see that, okay, this lock is still not available, and then from the running, because of the sleep, all 8 of them will go to the sleep. Now, when P2 releases, P3 to P10 will go through the same process again. All P3 to P10 will go to the ready because of the wake up. And of that, one of them will get the lock. And then rest of them has to again go back and sleep. So this shuttling between block to ready to running to block, this will happen, and this is a lot of process go through this context switching, and unnecessary context switching, which is in fact a huge performance penalty. So this is one disadvantage with this mutex approach. So another solution to this is that instead of before calling the sleep, we will add them to a queue. Add to a queue, and then just before wake up, you will remove the process, remove one process P, and you wake up only that particular process. So rest of the, so in case now P1 had the lock, P2 to P10 was in blocked, we will take P2 alone, only P2 will go to ready, P2 will go to running, and it will complete. Okay, then P3 will go to ready running. There won't be running to sleep again. So this will not happen. So this is another mechanism to solve the thundering herd problem. And another, the last primitive was the counting semaphore, or the semaphore. So this is like if you see the spin lock or the mutex, they are like only one of them can enter, right? Only one process can enter, one of them can access. Sometimes it happens that we have a certain resource like a buffer, and we can like the producer consumer problem that is discussed in the video. Uh, we our requirement was that producer, okay, let me do it properly. Producer, consumer. So we have this bounded buffer of size n. Okay, so the requirement is that producer will produce, and it should stop producing once the buffer is full, and the consumer should wait when the buffer is empty. Correct? So it's not that the producer write one buffer and wait for the consumer to consume it. You write it and let the consumer consume. That's not the scenario here. The producer can keep producing until it is full. Correct? So the number of resources we have here is n. So because we can allow the producer to write until the buffer is full, we don't, mutex is not sufficient here. We need something called as a counting semaphores. That is what we use in producer consumer problem. So so it is not like it is a 0 and 1 kind of a thing. So we have this semaphore which can take value which is greater than 0, 1, 2, etc. So in here, if the size of the buffer is n, we can have the semaphore size to n. So every time the producer writes, we decrement it. Every time a producer write to it, every time producer write, decrement. Consumer reads, increment. Okay, so this is the concept of counting semaphores. So we achieve this. We'll ensure that when no nothing is there, like when the buffer is empty. When the buffer is empty, so if you see s equal to n, when the buffer becomes full, the full will become 0, and further the producer will not be able to write. Same way, when the right, and when empty becomes n, consumer will not be reading from the buffer. Okay, so that is so to achieve this mechanism, we needed a semaphore which can have multiple, which can handle multiple, we can, wherein we can allow multiple reads and write to the resource. It's not like a single read or followed by a single, you lock it, do the read, then you release, and then you have to write. It's not like that. We can allow multiple reads and multiple writes. So for that, we need to have the value of s equal to n. Okay, so that we achieve with semaphores. So now I think let's go back to the previous year's question. Mm,
Excuse me, ma'am.
yeah,
Ma'am, I have a doubt. May I ask?
right. Yeah, please.
Ma'am, if the value of counting semaphore is given, then how can we calculate the maximum number of requests that can be for the tutorial section?
Come again. I mean, when the counting semaphore.
Ma'am, I have pasted it in the chat box. Can you please?
Is this from the current question?
No, ma'am, it is from 2021 session that is shown on the YouTube.
Okay, yeah, we can see that. So what? So it can go up to 0, right? So how many times we can enter? If the value is 6, before it block will be 6, right? So every time you enter the critical section, it will be 6 minus 1. So 5. 5 is greater than 0. Then 4, 3, 2, 1. So what is the check? Is it greater than 0 or greater than or equal to 0? That I need to confirm once. If it is accordingly, this number will change. Okay.
Okay, ma'am.
Yeah.
Ma'am, I have also
Yes.
doubt that in the assignment shown over here, so there are the two options that is given. That is, in the assignment today, it is asking that which of the following is a non-atomic preemptive. So, ma'am, as we know, test and set and CMP and swap are atomic, but it is given that test and set. So, ma'am, is it counted as a non-atomic or none of the above will be correct for it?
I cannot tell that. From the current assignment, I will not be able to answer.
Ma'am, but the test and set is not the correct word now.
No, I would prefer to not comment. Okay.
Okay,
Because I have
ma'am.
not seen the question also. I'm so sorry, yaar. I didn't see the question also. Okay, let's go to the previous year's question. Okay.
Return value of XCHG instruction is dash. Old value to new value 3 1 if operation succeeds and 0 if operation fails. None of the above. What is the right answer?
Ma'am, old value.
Yeah, so it is old value. Yeah. Trained and to design. Okay, so what is the answer? So what is the answer for the first one? Your friend wants to design a synchronization primitive and tells you that he would be better off if by strictly ensuring that the processes alternate the critical section. So it's like the first example that we saw, right? With turn equal to one, process one and process two. So in such a scenario,
What was the problem that we saw in that first software-based solution using the Stern variable? It will not, if you alter, if strictly ensuring that the processes alternate between each other, then if there are two process P1 and P2, and by any chance if P2 arrives first, then P2 will not be able to proceed until P1 executes. So this doesn't meet the progress criteria, correct? So this might not satisfy the progress requirement. Now the next one is bakery algorithm ensures that no process is stopped. So it's a bakery algorithm is a multi-process synchronization mechanism. So it ensures that there is no all the critical section requirements are met by the algorithm. So it is true. So the next question is true or false. Message passing is slow compared to shared memory. Is this true or false?
Ma'am, true.
Okay, so true or false? Message passing is slow compared to shared memory and more error prone. Is it true or false?
I'm false.
So one part of the statement is true and the other part is false. So the statement is false, correct? See, message passing is slow when compared to shared memory, but it is not error prone. Okay, so this is false. Then IPC with message passing. The shared memory is in an interprocess
User space.
communication is in message passing. Shared memory is it
User
used
space.
with message passing. With message passing, it is in kernel space.
Ma'am, means shared memory is in user, but in message passing is it with kernel space.
Yeah. No, no. See, IPC. See, both of them have shared memory. Okay. The other mechanism is called shared memory. This is the message passing. In message passing, that the common memory between the two process is in the kernel space.
Okay, ma'am.
A certain application
The meeting ஓடிட்டு இருக்குமா அதுக்காகவா
Yeah, so basically, the P operation is the decrement operation, and that is the lock, and V is the release, the increment. Okay, so P will be done before entering the critical section, and V will be done after the critical section. So initial value of S is 10, right? So 5 P operation means P is decremented 5 times. So it is initial value is 10, 10 minus 5. Again another 20 decrement operation, minus 20, 1, 2 increment, minus 18 decrement, plus 5 increment, minus 10 decrement, plus 1. So what is this value?
Ma'am, minus 34.
Minus Okay, so the final value is minus 35. So what P does is P will do S minus minus and V will do S plus plus.
Ma'am, 4.
Yeah, so how the P operation and V operation works is, so I think I didn't, while S less than or equal to 0, you wait. If S is less than or equal to 0, you wait. Otherwise, you decrement. This is the P operation. The V operation is S plus plus. Okay, so initially the value was 4. So we will enter once, the value becomes 3. We will enter, so S minus minus will happen. Then again, so this becomes 3, correct? So again, now S is less than or equal to 0, no, correct? So again, one more request will be met. And S will be decremented, which will take it to 2. Now, while 2 is less than or equal to 0, 2 is not less than or equal to 0. Again, it will enter the while and S will be decremented, which takes the value to 1. Now, is S 1 less than or equal to 0? That is also false. So, we will enter the while loop and then S minus minus, which will make the value to 0. So now S is less than or equal to 0. That is true. So now it will wait. It gets blocked. So how many requests are met? 1, 2, 3, 4.
So the answer is 4. Okay.
Next question. Hmm.
Ah, ma'am, the answer is true. Ma'am, please said Madhu Chhatri to mute their mic. It is causing unnecessary disturbance.
Okay, let's see the first one. Is it possible to share the messages without attaching the shared memory with the address space of the calling process? So the statement is true or false.
I'm
So
true.
this is it, it is it is possible to share the messages. It is possible to share the messages even without attaching the shared memory with the address space of the calling process. So actually, before for accessing the shared memory, we need to attach it. So without attaching it, we will not be able to access it. So the statement is false. Okay. Peterson's solution is a synchronization mechanism for maximum of dash processes.
Two processes.
Yeah, it is two processes. So this let me write the last option. We'll see. Okay. So atomic operations like test and set ensure that they are executed in a single cycle. They can be executed in multiple cycles. No other memory instructions is executed while this instruction is executing. They can be executed in multiple cycles, but no other memory instruction to the same variable is executed while this instruction is executing. And last option is no other instructions execute in the background while this instruction is being executed. Which option is correct?
I'm option C.
Right. So option C is the right answer. So another question is test and set operation. Sorry. Instructions. So this question is not from previous year. So the test and set instructions that provide hardware synchronization does not guarantee mutual exclusion,
Bounded weight.
progress, and bounded weight. Yeah, bounded weight does not guarantee that. Now this one, following program consists of three concurrent processes and three binary semaphores. So binary semaphore is nothing but semaphore that can have value 0 and 1. That's it. Semaphores are initialized as S0 as 1, S1 as 0, S2 as 0. How many times P0 will print? O. So for P0 to print this one, this is the semaphore that is locking it. Okay. So initially the value is 1. Okay. So if it is 1, it will enter the critical section and it will print 0. So one time it is printed. Now after that, S1 is released. So the value of S1 now becomes 1 and S2 also becomes 1. Okay. Because only P1, P0 can proceed initially, because initially the value of S1 is 0 and S2 is also 0. So both P1 and P2 is waiting. Now immediately when S1 and S2 is released, P1 will enter here because now S1 is 1 and it will release S0. So now S0 will become 1. Okay. Again, if we go to P2, P2 is waiting on S2. So now the value of S2 is 1. So it will enter the critical section and it will again release S0. So the value of S0 will become 2. Okay. Now again, if we come back here, we are waiting. So S0 will be decremented once and all will be printed. So S0 will become 1 now. Now again, the second iteration, it will be printed 0. This will become 0. Okay.
Yes, ma'am.
Right. So that's all I have for today. If there are no doubts, we can close the session.
No, ma'am.
Yeah. Thank you all. Thank you for joining.
Thank you, ma'am.
Bye. Bye.
Bye.